Here we go. Okay. So this is implicit differentiation. The reason it's called implicit is kind of spelled out in the book. If you have an equation that has like x squared and y squared, you can explicitly solve it for y, and you might have multiple parts to actually make it a function, right? Because like things like a circle are not functions. There's ways to do it. The cool thing is when we're taking a derivative, we don't have to go to the algebra to get it equal to y. We've got a technique that will implicitly give us the derivative. And it's really, other than putting in a marker for it, it's really nothing new. All the rules we've learned about taking a derivative of x, they apply to taking a derivative of y. We just put a little extra marker saying, hey, this is a derivative of y. When we do it with x, we don't put a marker. We just know it's the derivative. Okay. So here we are at 2.6. And again, I don't look ahead too far, but we've got 2 more sections in chapter 2. I've got them all set to be due on the Wednesday for the review. Again, I'll move them because maybe during the review you find some things that are helpful, but I just kind of put the first due date to get you close to there. But it's good because with the due date comes, then it will give you all the answers, and it makes it easier to review for the exam. So let's do it what we can to at least get everything in chapter 2 pretty much finalized by the weekend that we do that review. We'll get into chapter 3, we'll do the same thing, and then we've got a day to do the exam review before we get to test number 2. And our goal is to do well. So we were going to rethink how we do the derivative. So we'll start with something we've already been doing to kind of make this a little clearer. We've been taking derivatives of functions. Where is my... Oh, I have to plug it in. That's why the pen doesn't work. Okay. There we go. Okay. So we've been using just sort of prime notation, and we say, okay, come here. Oops, back up. So we just, come on. I got a new, I know what it's doing, maybe. So we kind of just did, this is the derivative of f of x, and we went ahead and take it. What we're going to do today is think of f of x as y equals 2x squared minus 3x plus 4. So, and I'm going to jump right into using this explicit differentiation. So what we've really been doing is we've been taking the derivative of y with respect to x. So there's 2 notations we could use. I'm going to do this one because it's, I'll use both, but we could think when we take this derivative of y, we're taking the derivative of y with respect to x. And if since y is just y to the first power, if you were to actually take its derivative, what would it be? 1 comes down in front. 1 minus 1 is 0. Y to the 0 is 1. So it's really just 1. But what we want to think is it's 1 times dy dx. So I'm going to put this little 1 here to represent that I actually did take the derivative of y. We've been doing this, but we just didn't explicitly say that's what we were doing. Now I'm getting the derivative of y with respect to x. And so then on the other side, I just take the derivative of x, and I don't put any special marker. We could put d dx, so I'm taking that's, but we don't have to, so we don't. So on this side, we could take the 2 times 2 is 4, subtract 1 from the exponent, that's x to the 1. 1 times negative 3 is negative 3. 1 minus 1 is 0, so that's x to the 0 is 1, and then the derivative of 4 is 0. So that's really what we're doing, and that's all we're going to do with an implicit differentiation, but it's going to look a little bit more complicated, obviously. But does that look any different than really anything we've done so far? Not really, except for that dy dx. Now you could have also done it this way with this notation. We could have said that the and I guess we've kind of been, I've got to fix this thing, but I got a new tablet that's more portable, but I've got to set it up for portability. So we could also do y prime is equal to 4x minus 3. So you can, whichever feels more comfortable to you, you can use as your marker y prime, or you could use dy dx. I'm going to kind of typically use dy dx because it's clearer to me, and if I do y prime, it kind of blends in too much. So why do we need to do this? Well, there's a couple places. One place is when we can't solve it for y equals, right? So we could do some algebra, but we can get it to y equals 25 minus x squared. But unless we take the square root of both sides, we'd actually have two different pieces, right? And that would be two different pieces of the function. That actually would be functions. We'd have the top of the circle and the bottom of the circle. But with the implicit differentiation, we don't have to do that. What we do is we just go ahead and start taking derivatives, and we'll just kind of walk through and see how this works. So with x, we just take its derivative, right? The 2 comes down. It's going to be 2x. Subtract 1 from the exponent, 2x to the 1 power. When I get to y, I'm going to do the same thing, except I'm going to make a notation that I'm taking the derivative of y with respect to x. Okay, so the way I do that is, what's the derivative of y squared? Well, the 2 comes down, y to the first power, and then I just have to say, but this, when I did this, I'm taking the derivative of y with respect to x. So I use that. You could use the y prime, but you could see how easily y to the first power and y prime could look the same. So I put this little nice big thing. And then what happens when we take the derivative of 25? You're right, it's 0. So we actually take the derivative of every little piece in there, every little term. It's a constant, it's just 0. But we're not quite done. Now all we need to do is solve for dy dx. And that's going to give us what the derivative is supposed to be. So solving for dy dx, we want to get it by itself, right? We're going to subtract 2x from both sides. And so we end up with 2y dy dx equals negative 2x. And then we'll divide both sides by 2y. And so we get that our derivative, dy dx, is equal to negative 2x over 2y. So it feels a little strange because we have an x and a y on the same side, and we're used to dealing with functions that don't, but it is what it is. So this is the derivative. It is still the rate of change, right? Because that is a slope. It just involves two variables because we're dealing with a relation, not a function, right? X squared plus y squared is not a function. And that's all there is to it. Okay. We're going to see the product rule applies, chain rule applies, so we'll look, it can get a little bit more complicated, but
whenever you put in the dy over dx, you always just multiply it by the y.
Yes, it gets multiplied. So think of it as being multiplied by the actual derivative of the y. So had it been y to the third, the 3 comes down, we would have had 3y squared times dy dx. Okay. Yes, good. And it is multiplication. It's not some funky unknown thing going on. It's just multiplication. Good. And that's why when we solve for it, we just kind of treat it as if it's another variable or it is another characteristic. It is the rate. Okay. I think on this, a lot of them, what they will do, they will ask you to find the implicit derivative, but oftentimes they will also ask you to find what is the derivative at a particular point on the graph. And I think I wrote over my question. I did, but they'll say something like, find the derivative of y. And that, again, notice how we're mixing notation here. Y prime, could have said dy dx, but using function notation, find the derivative of y of 4, so that 4 is an x value. The 3 is a y value. well, actually, yeah, so if the function y of 4 equals 3. So notice we didn't solve it for function notation, but that's kind of what we're using. But it's really just telling us it goes through the point 4, 3 is on this, and so let's find the derivative at 4, 3. So what we do is we wait and do this at the end. We just come over here and say, well, they told us x equals 4, y equals 3. So we just plug those into the derivative and find that dy dx at the point 4, 3 is going to be negative 2 times 4, 2 times 3, which is, I guess you can reduce it a little. Well, we could have reduced it up here, canceled out the 2's, right? I guess why don't we go ahead and do that? So we're going to get that this one would be negative 4 over 3. Okay, so that's the derivative at there. So you'll see questions like that. Some of the questions, we'll look at one where it asks for the tangent line. We're going to do that together. Again, what's the tangent line? The slope of the tangent line is the derivative. So they give us a point, we plug it in, that will give us the slope. And then we've got y equals mx plus b, whatever we figured out m, we put the point back in and figure out what b is, and we're done. Okay. We're not able to use our graphing calculators for these because it's not a function. Desmos will actually do these for you, though. You can, because Desmos doesn't need a function, and it's kind of cool. It'll draw the circles. It'll draw it all. So if you want to play with that, you can do that. I think Desmos also has a derivative function, so you could probably take it further than what we are going to do here. Okay. So now we're going to get into basically the same thing. That's the technique. Whenever we take the derivative of y, we just put a little marker, dy dx. Multiply it by that derivative. If x is just by itself, we do that. So this is kind of similar to what we just did, except this part over here, 6xy, is going to look a little different, because what's going on with 6xy? X and y are being multiplied. We're going to need to use the product rule there. So it looks a little tricky, but again, as you go through this, this is where it kind of started clicking for me what the product rule really was. So let's go ahead and take this derivative. So x to the third, 3 comes down, subtract 1 from the exponent, so we get 3x squared. Take the derivative of y, the 3 comes down, subtract 1 from the exponent, we got y squared. But we took the derivative of y instead of x, so we say, hey, okay, we know. We took the derivative of y with respect to x. Just put that marker there. And then that's what we're going to solve for. Actually, sort of, but we're not done yet. Now we get to the other side. It was nice when we just had 25, a constant, take its derivative at 0. But in this case, it's not going to be 0, right? We've got 2 variables there. So let me come over here and think about this. And let me see some new notation I'm going to use. So remember when we're doing a product rule, the 6 we can just kind of ignore and say at the end we'll multiply by 6. So we're really taking this derivative. So the product rule says take the derivative of the first part with the second part unchanged, plus take the derivative of the second part, I'll use this notation here, times the first part unchanged. So when I take the derivative of x, what do I get? 1. Yeah, and the 6 is down here too, so we'll just kind of put it on the outside. So derivative of just x, 1 comes down, 1 minus 1 is 0, so that's just 1. So we've got 1 times y, right? And the 6 is out here. And then when I take the derivative, so that's that part. When I took the second term, derivative of y is also 1, right? The 1 comes down. But this is where I put my dy dx because I took a derivative of y. And then x, unchanged. Nothing happens to it. And then I could distribute that 6 through, and that's what that piece is going to be. Does that make sense? The product rule here. Okay, I'm gonna, maybe I'll rewrite it in red. So it really becomes 6y plus 6x dy dx on this side. And again, I If I left myself a little room, it'd be up on the line. We've got the derivative part done. Now we just need to solve for dy dx. And notice we have a two of them, right? There's two dy dx's. So we're going to have to get them to the same side. Everything that doesn't have a dy dx, get it to the other side, factor out a dy dx, and then divide by the stuff that isn't dy dx. And that's how we solve it for a single dy dx. So it's, again, it's algebra as we do it. So what I'm going to think, okay, so we're going to want this thing and this part here all on the same side. And actually their terms go with it. So I think I could subtract 6x dx dy from both sides. So minus 6x dy dx. And that's going to come over here. At the same time, I'm going to get this 6x squared over to the other side because it's in the way right now, really. Minus 3x squared. And we'll put it over here. Minus 3x squared. Okay. And so what we end up with is we're going to get 3y squared dy dx minus 6x dy dx. On this side, okay, that canceled with that. So then we get 6y minus 3x squared. Okay. So the second to last step is to factor out the dy dx because we got two of them, so to bring it in the front. See if my pen will let me write down there. I don't think it will. So I'll do it over here. So, okay. So we have this and this get factored to the front, right? So it's going to be up here. This is what's left. So let me give myself a little more room. I'm going to erase this sort of side work. Still there in the recording, so that'll be posted. Should be in your notes already. Let's just get rid of it all so it doesn't confuse us. That's good. And so we get dy dx up front. We've got 3y squared minus 6x equals 6y minus 3x squared. And then we just divide both sides by all this stuff over here, this 3y squared. Right, to get that to cancel out. And so I'll just write the final answer. We get dy dx equals 6y minus 3x over 3y squared minus 6x. Okay, so you'll notice with this, oftentimes we're going to end up with fractions.
That's experience.
Where did I miss? Oh, thank you. See, that's what, put it in the corner. I didn't see it. Messed up. That's why it's good to. You could also do that too, make it more pretty. Again, if I can leave it as close to the original, I sort of try to do that, not simplifying too much. WebWorks should be able to handle it. It's got a calculation tool, and it's because then you can see what you've done. Once you start taking out the 3 and canceling, then it looks different than what you started. You don't see those, you don't see from the original where some of that stuff's coming from, but I see, okay, 3x squared, that came from those exponents. 6 is coming from the 6xy. I see where those are. As soon as I reduce them, nothing matches up. And again, for me, it's kind of, I don't know if there's two schools of it, but I know that most professors I talk to disagree with how I do it. But you got to see the pieces, That's what math is about. It's about the pieces. It's about the patterns. It's about where things come from. And so simplifying, you lose that trail. Okay? And this is pretty much what it is. We're going to do a few others. There was one with a trig function that I thought we might do together from the homework. Like that. So this one, we're also going to, you see we have a chain rule because we've got something inside the sign. So we've got to take a derivative of the sign, which is an outside function, and then we got to take a derivative of that inside function, x plus y. Again, it's not overly complicated, but we have to apply that chain rule. And then on the other side, we've got a product rule again, right? Because we've got y squared times cosine x. So we've got to follow through it. We can't just take the derivative of y and take the derivative of x and multiply them together. There's this process. Take the derivative of one with one unchanged plus the derivative of the other with the other unchanged. So, following through with this product rule and the chain rule as we go. So let's see how this works for us. Okay. So, and again, you sort of transition into, sometimes I find if you try to write out too many things of too many steps, it's actually harder to do. So on this side, when I take this derivative, hopefully I can see that chain rule, so I sort of cover up this inside. What is the derivative of sine? Cosine. Directly cosine. It's not the, so this is cosine. So I'm going to write that down. So I took its derivative, and the inside stuff does not get changed, right? This is the inside stuff. But then I also remember with the chain rule, I have to take the derivative of that inside stuff. Okay, so I have to take the derivative of x plus y. Not too bad, but so I take the derivative of x, and what do I get? 1. Good. I take the derivative of y, what do I get? 1 dy dx. I don't have to write the 1, you're right, but I'll put that just to remind myself that I'm actually taking the derivative, because otherwise I get a y squared and I forget that actually is what I did. I took the derivative of y, it's 1, and then I've got the marker dy dx. And fortunately it's out here, but you can see it's going to be, maybe solving is going to be a little messy, but we'll get there. Okay, so that's that side. On the right side, we've got a product rule thing to work with. So again, I'll kind of just start doing this as best I can. So I want this derivative. I need to take the derivative of the first part. So y squared gives us 2y dy dx, right? We'll just put that right in there. Times the other function, the other product, unchanged. So that's just a cosine x. I don't take its derivative. Okay, start seeing how I'm more and more internalizing the product rule, because actually writing it out might make it messier. And then I take the direct derivative of the second part, right, the cosine, and times y squared unchanged, right? You could put the y squared first if you want. Maybe it's easier to do that. Y squared, so I didn't do anything to it. Cosine, what's the derivative of cosine? Negative sine. So I said, oh, shoot. Oh, well, I'll scratch it out, put my negative sine. And sine of what? X. Now, again, if you use the chain rule, the derivative of x is just 1. But if it was a sine of y, or if it was cosine of y, remember, I'd have to actually apply the chain rule. I'd get it changing to sine of y, and then I'd have to put a dy dx out here because chain rule. Okay, so I think there's one that we're going to look at that particular case. Okay, so it's kind of a mess, but again, what I come back to is all I need to do now. I've got the derivative. I just got to get the dy dx's together so I can factor them out. Everything that doesn't have a dy dx to one side, everything that does have a dy dx to the other side. Hopefully it's fairly easy to factor it out. You might see that this is 1 plus this, so actually I might want to distribute the cosine of xy through here. So I will do that. so that I can get to this dy dx. So it's multiplied times 1, and then it's multiplied here. So what I get is 1 times cosine xy is cosine x plus y, and then cosine xy times dy dx, and notice this plus here, is going to be plus cosine x plus y dy dx. On this side, we don't have to distribute really anything, but we just got, let's do it as 2y cosine of x dy dx, kind of move it to the back, minus y squared sine of x. Okay, save myself a little bit of space. Hopefully this doesn't throw anyone off too much. Anything that doesn't have an x, I'm going to move this over so it's positive on this side, right? It's going to become negative on this side. I'm going to do the same thing. I'm going to move this one to the left side, subtracting it, so it's going to become negative over there. So I'm going to rewrite this as the cosine x plus y, and that's this part here, dy dx. I'm going to bring this over so it's going to become negative because I'm subtracting it from both sides. 2y cosine x dy dx. I've got a minus sign. I'm going to bring this cosine here over, so it's going to become negative. So I'll have negative cosine x plus y minus y squared sine of x. Again, I look at my dy dx. That is going to get factored to the front, both of them, right? So those come to the front. You can see the two terms that are left. What are we going to do with those two terms? They divide to the other side. We divide them out. So what we get is that dy, let me see if I can, no, I don't want to do that. Let's come back to this. Well, maybe I'll write it up here. I get dy change colors. We get dy dx, right, that's this part, is going to be equal to this side here divided by the stuff that's left over here. So you'll get minus cosine x plus y minus y squared sine of x. That's all in the top. And in the bottom is going to be cosine x plus y minus 2y cosine of x. And again, if they wanted the derivative at a point, or they wanted the tangent line, we could find the slope by plugging in x and y and getting a numerical value for that derivative. Because remember, what is a derivative? Slope of the tangent line, instantaneous rate of change at a point. But what we've got is this, we've got it sort of as a, well, I guess can't call it a function, but we have it as a expression, so that we could find it really at any point that is on that original graph. Is that okay? I know it gets a little, it's watching all the pieces. I wish I had more paper, but I guess I can make another sheet, but it's all over the place. Okay, but just kind of, yes.
I'm still like the green part. Like I don't understand how you simplify it down.
I didn't simplify, I took the pieces. So this piece here minus this piece. So I factored out the dy dx. So it's kind of like we had 3x squared plus 3y squared, and I'm rewriting it as 3x squared plus y squared. Okay, so I'm just taking a common factor, factoring it out,
Okay.
and then dividing over. But you're right, that takes, once you do it enough times, it starts to make sense, but it doesn't really seem natural because it's a backwards thing. We usually distribute. This is undistributing, and it's not something we do on a natural basis. Okay? But that's, you know, you could see you're going to use probably a lot of paper for these. But at the same time, as you go through them, they start clarifying product rule, chain rule, because you start leaving these markers of dy dx. That's when you, and some of you might say, well, hey, let's go with d dx when I took a derivative of x, so I can tell the difference between a derivative and the thing I didn't take the derivative of. In a way, it's kind of cool. Okay, I'll try to maybe write smaller. So this is one from the homework. And the 3 is the question number. Actually, this has 4 parts to it. So I took one of the parts and I said, let's kind of go ahead and do this together. It's a little bit, it should be a little cleaner because it doesn't have the messy stuff. There's no chain rule in this one. Well, actually there is. I lied, right? Because we've got a cosine of y. We're going to see a chain rule here, okay? There's one product rule. That's right here at the beginning. We've got 2x times cosine of y. So we'll have to use the product rule there. So what's the derivative? So product rule, remember, derivative of one of the terms with one unchanged plus derivative. So derivative of 2x is just going to be 2. And then cosine y, so that part didn't get changed. I also, as I do these, I'm going to put a parentheses around. Again, you don't have to. The book doesn't, but it's really an input. And then this, it's not this plus, but remember, I'm now going to take the derivative of the second part. So that's plus 2x, right? We didn't take that derivative, times the derivative of cosine of y. When you're taking the derivative of cosine of y, you've got a chain rule thing, right? You've got to take the derivative of the outside. What's the derivative of cosine? Negative sine. So I'm going to actually just put it in here. So it's negative sine of y. And then from the chain rule, because we haven't actually taken the derivative of y yet, y is inside the function. We took the derivative of sine. What's the derivative of y?
Well, 1
dy dx, or y prime if you want, but like I said. So that's where the chain rule kind of, it seems kind of weird because there's nothing left. Actually, if you want, it's really 1 dy dx, because we took the derivative of y. Had it been y squared, it would have been 2y dy dx, right? Y cubed, if that would have been inside, it would have been 3y squared dy dx. Sometimes if it's more complicated, it's actually easier to see. Okay, but we had to do that chain rule, and that's one thing people will miss is they forget about the chain rule. Okay, and that's just for this first term. Yes, sir. Okay, now we start taking the second term. Yeah, so that's where. Yeah. So that's kind of, because you see that plus and you start thinking, how is that part of that? No, this is all from that first term. The second part is a little easier because it's just 2. It's not a product rule. And again, I don't like it when they don't put parentheses because it's, you'll see this part here, right? So now the 2 just kind of, it's a constant. What's the derivative of sine? Cosine of 2y. And then we've got the chain rule. We take the derivative of the inside part. Derivative of 2y is 2 dy dx. dy with respect to x is dy So we got the marker there. And so then we're going to get 2 times 2, so it'll become a 4. You could do that part. We'll get there. So far we're doing okay? You start to see each piece we have to do. So we did a chain rule here, and then we have our equals. So that this part came from here using the chain rule. This part, we're just going to get 2 derivative of sine is cosine of y, and then the derivative of the inside part, dy dx. Dy dx, not dx dy. See, that's, okay. And actually 1 dy dx. Had it been x, we actually do that. We take the derivative of x2, but it's just 1, so we don't write anything. So we don't get used to calling it the chain rule. But since it's y, we have to have that marker. Doing okay? Okay. And now this is where it just gets kind of a little messy. But again, what I always like to do is, you know, with the different color, okay, here's a dy dx, because these are all the things we have to get together. Here's another dy dx. And here's a dy dx. So all of the dy dx's have to get to the same side. We factor it out, and then there's this big chunk of stuff, and then we divide it back to the other side. And so that's why we'll always end up with usually a division. So I look this part, oh, it can just stay right here. Let's see. This actually is a negative, so that's going to, just to clean it up, I'm going to change this plus into a minus, and then just kind of get rid of that. So this is a multiplication, so this whole term, what I'm going to do with it is I'll move it to the other side. And then we'll clean this up a little bit, but it also moves to the other side, or maybe it would have been easier to, however you want to do it. Again, but you've got to get everything with the dy dx to one side, everything that doesn't have a dy dx on the other side. So I guess I'll move these two over here. So we get 2 cosine y. This is going to go, this is going to go. Okay, so I'm going to put the equals here. Now, when we move it to the other side, how we're doing that is we're doing the opposite. We're either adding or subtracting. We're doing the opposite. So if it's negative, when it gets to the other side, what's it going to be? Positive. So that's, rather than writing down each step that I'm adding that to both sides, I just said, okay, to move this term here, when I move it over, it's going to become plus, and I'll just write it out, plus 2x sine of y. Oh, wait. Oh, yeah, that's from this part here. Okay, so that's why I was always going, did I write sine of y dy dx? And since it's in the front, you don't really need that plus sign there, but I just wanted to emphasize that it was negative, and I moved it over and made it negative. This second part here is positive now. When I move it over, it's going to become negative. And just so things come together, I've got a 2 times 2. That's the one time I do, okay, let me simplify that, because otherwise I've got, you know, just, it doesn't look right. So 2 times 2 is 4, and then I've got cosine of 2y. Now remember, this is on the other side, and then I've got my dy dx. And then I've got the piece that was already there. It was positive. It's going to stay positive. 2 cosine y dy dx. And I just kind of like to think of it, you know, everyone's going to give a dy dx on the right-hand side. We're going to factor out the dy dx to the end. It becomes a single dy dx. Everything else is now in a parentheses, and we just divide that over. And again, it can become tedious, and again, if it's helpful, you can write each thing. But what I'm going to do is I'm going to say all of these pieces are just going to be in the denominator. They keep their same sign that they have now, but they're going to be divided over, right? Because what happens to the dy dx? They all factor because they're multiplying. They factor, maybe to the front or to the back, however you want to do it, but they factor out of that. And let's see, I might be able to write this, see if it helps. So we have 2x sine y minus 4 cosine 2y. We're doing on time, wow. Dy dx got factored out, plus 2 cosine y, and then in the back is dy dx. And I always have to do a check on myself. I say, okay, now if I distribute it back, oh, that's what I got. So because undistributing feels a little weird, because we're used to distributing things to simplify or something. But we're undistributing, and that's all 2 cosine y. So now all of this stuff here is in the denominator over here. We just divide it over, and it's there, and that's our answer. Okay, so you'll see that, and there's 4 of these that are very similar, but they change where the y's in and cosines. So you get practice with 4 of these.
For the exam, do you have to simplify the fraction?
No.
Okay.
And again, I don't write the exams, but remember, it'll be very similar. There'll be like 8 multiple choice.
Yeah.
You have to be able to recognize it. It's possible that the person who wrote the exam might do a little bit of simplification, but you should probably be able to see that. On the open free response ones, I'll take a right answer is a right answer. Yes.
Will it just ask for like dy or dx? Or?
Oftentimes it does. Sometimes it will say, then what is the derivative at this point? It gives us an x and a y, and then what we have to do is plug it in and get it down to a numerical value. The other question that gets asked is, what's the slope of the tangent line? Same thing, plug in the x and y they give us. Sometimes they'll ask for the equation of the tangent line, get the slope, but then we have to finish y equals mx plus b and solve for b.
So is this the same thing as slope in just a different form?
It is. It is a rate of change. So yes, we are getting slope, exactly, dy dx. It's exactly, so that's where kind of things start clicking. That's what we're getting, but we're dealing with things that are actually not functions, or might not be functions. Here's a more complicated one, but implicit differentiation. You'll see it again with related rates, so we'll keep practicing. I think related rates is actually next, but we'll keep moving with it. I thought that was going to go faster. Yes, right.
Yeah, there we go. Thank you very much.
We're hiding in the couch.
Yeah.
I just had a question about, I did some of the problems and I didn't do them correctly, so I was just wondering where I went wrong.
Okay. From the test? Or
No,
from, no.
from right now.
Okay.
So this one, I got like the same exact answer except negated. I'm not really sure where I went wrong in my steps.
Over, so you got the negative 6 over here. It should be negative. Well, maybe I went too fast. So it might not be. That was, yeah, I got negatives as well.
But we got the same answer but negated.
Okay, I moved. Subtracted that. Subtracted that. I think you moved everything this way, I moved everything that way. If you put a negative on the top and a negative on the bottom, that answer will match this answer.
So it's the same
Or
answer.
negative, right? It is. Yeah,
Okay.
that's the difficulty with some of these things. We could, because you went left and I went right, we actually have the same answer, but it doesn't look right, yes.
I see. Thank you.
Good job, good job. Just put in your name. That's all I asked you to do. You did it, but you didn't tell me you did it. Yeah. Just, I forgot what I was supposed to do. Just click, go back and there's a screen that's still open. When I say start your name or actually, it shows up that there's a submission. Possibly. That's why this one.
Supposed to be plus, or does it stay negative?
One of them, when we took the derivative, so the right one, the cosine x, when I took its derivative, that's what that we negative sine x. But the first part, using the product rule, I didn't actually take the derivative of the cosine. I only took the derivative of y squared. Does that make sense?
Yeah, and then for this, because at the bottom it's cosine x plus y third of y dx minus 2y cosine x. What's supposed to be minus cosine on each side, or do you have that?
This one I subtracted over.
Yeah.
That one I had to subtract over.
Would it be plus 2y cosine? Since you're moving it to that side?
Well, actually, I moved it to the left side.
Oh, you moved it to the left
So
side.
I subtracted it from both sides.
Okay, yeah, that makes more sense. Alright, I was just lost. I was like, okay,
Yeah,
2y.
I might do a few of these just separately on the.
Yeah, and so I got lost because I was like, okay, so okay, yeah, that makes more sense then.
Okay.
Alright, thank you.
You're welcome. Sir.
Yeah, means I have few doubts. So should we come like to your?
Sure.
You have he mailed you and you have I guess MAT 170 students coming.
Yeah, they have a test today, so I'm not sure how soon they will.